So we want to talk about another method of finding the volume of a solid of a revolution, and this is the shell method we're going to look at. And we've got the formulas here, and this horizontal and vertical axis of rotations, revolutions that we did with the disk washer method. Let's take a look at how this gets set up. So I'm going to take a look at a example here to see where we get these. We'll do the X and the Y axis here, and so let this be the Y axis here, and let me just have a region, and I'm going to have the curve look something like this, and we're going to take this region in the first quadrant, and let's say this is let's just say we're going to go from A to B. We'll let A be 0 this time and B be this location. So A is 0, B is wherever this curve hits the x-axis at. Okay, and we're going to rotate this about the y-axis. And we've seen something like this before. If I rotate this about, I hope you see that we're going to get a dome-shaped structure, maybe more like the nose of a rocket or something like that. This is the kind of shape we're going to get. All right, and it's going to the y-axis right there. Okay, so that we're going to rotate this region about the y-axis. We're going to get this three-dimensional solid, and we want to find the capacity, the volume of this. So what we're going to do this time is, when we're doing the disk method, since we were rotating about the vertical axis, we would be integrating with respect to y, and we would have horizontal rectangles. For the shell method, we go ahead and stick with vertical rectangles. So notice, because of that, we're going to integrate with respect to x. We're going to integrate with respect to x. And so what I want to do is rotate this rectangle now about the y-axis, and notice we're not going to get a thin circular disk. We're going to get something else that we call a thin circular shell. Okay, and there's some thickness to this, I guess, right? Thin shell, and it's got draw these hidden lines down here. Okay, so this rectangle right here is here, and it's going about, right, coming right out the center here, up here. This is the y-axis. Okay, so if I take this rectangle, rotate it about the y-axis, goes back into the page here. All right, we're going to get this thin cylindrical, what we call a shell. Okay, used to be some old car filters that were this shape instead of the rectangular ones a lot of the vehicles now have. They had these round ones, right, these cylindrical shaped ones. Okay, so what I want to do is I want to find the volume of this shell, and then I'm going to integrate from A to B all the different shells. So each rectangle will create a shell. So it's a little different. Our objects we're looking at are these shells, and we're finding the volume of each shell, adding them all up to approximate the volume of this whole thing. Okay, now before I do that, I want to illustrate this. Again, a student of mine in a previous semester has constructed, first of all, this object is a solid, right? It's this region, rotating it about. We get something that looks kind of like this. I didn't quite, should have sketched it so it was perfect, but it's not quite that way. But so roughly this sort of shape, right? This dome shaped thing. And so the question is, what's the volume? How much material is inside this in cubic units? How much material is inside this object? Now, the idea we're going to approximate this shape with is we're going to approximate it with a thin cylindrical shell. Now, the shell that I get from this this rectangle here, okay, I rotate that rectangle about, it's going to form this thin cylindrical shell. Do you see that? This is the thin shell. This is what I've drawn down here. Right, this is the thin cylindrical shell, and it's got this, it's got the hole right through it, right? And so we want to find the volume of this thin cylindrical shell. And when I do the volume for each, rectangle, here's one rectangle, and then I will have, further out I would have this rectangle here, and so on and so on. And as I look at all those rectangles, he's put in this little thing, right? This is the shape we get, which is supposed to match up with that. Now that's the approximation. Of course, we know what we're going to do. We're going to integrate, and so we're going to take the limit as delta x goes to 0, and we get more and more of these thin shells with a thinner and thinner. The delta x is the width of each shell, the thickness of each shell, thickness of the rectangle, right? And so that's sort of the idea behind what we're doing. We're approximating that with these shells. So I need to find the volume of the shell, though. Okay. So the way I'm going to do that is this. I'm going to take this shell, and I'm going to cut along one side here. I'm going to take my scissors. Here's a pair of scissors right here, right? I'm going to take my scissors. I'm not really going to do this, but I'm going to cut right along up there, and then I'm going to unroll it. Of course, this one's rigid. I wouldn't be able to unroll it, but imagine it was a malleable material. So I'm going to cut right along there, and then I'm going to fold it open. And when I do that, I'm going to get what I call a rectangular slab, if you will. Okay, and what I'm interested in then really is the area. The thickness of the slab is just delta x, which is the thickness of our original rectangle, okay, and the thickness of our shell. But I want to know is the area of this rectangular surface here. What's the area of this, right? Well, I need is what? To find the area of a rectangle is length times width, or length times height. Now, what about the height here? Well, the height is the same as the height of the shell, right? We'll call that h of x, and so that's h of x, which is the same as what? The height of the original rectangle in this case, assuming that this function is, say, h of x, then that would be the height. But whatever the function is, the h of x would be equal to that height. And then what about the length here? What I'm going to do is, when we do this rotation, I'm going to say that there's some distance from here to here. Now this distance is x, but in general I'll just say this is p of x because it may not be x. But in this case, p as a function of x is equal to x. That's how far out this arbitrary rectangle is. And that's important because that's the radius of this thin cylindrical shell, p of x. Okay. And if I were to unroll this, right, then this length of this slab here is equal to what? The circumference of the shell, right? It would be the distance around this shell, right? Well, what's the distance around? That's the circumference of the circle, right? Circumference is what? Pi times the diameter, which is the same as 2 pi times the radius. And if the radius is p of x, then this is 2 pi times the radius. We're calling that p of x. Okay. And so the area as a function of x would be 2 pi p of x, length, times height or width, h of x. And that's our cross-sectional area. It's the area of our thin cylindrical shell. And then we multiply it by its thickness, we get the volume of the shell, right? But there's the area of the cross-section. So I'm going to integrate that with respect to x, and we get, right, here it is, right, from a to b, the integral p of x, h of x dx. The 2 pi is a constant multiple, so it would come out. And similarly, if we're integrating with respect to y, we would have these as functions of y, both the height of our cylinder and the inner radius. So the height is h, and that inner radius is what we call p. Okay, so let's see how this works with an example or two here. And also with this example, we'll kind of get an idea why we want to even use the shell method and why don't we just use the disk method. With this example, you can see a problem with using the disk method and an advantage for using the shell method. So we're going to rotate the region in the first quadrant bounded by y equals x minus x cubed. That's this graph right here. And y equals 0, which again y equals 0 is the x-axis. And we're going to do that about the y-axis. So here's the y-axis right here. And we'll rotate that about the y-axis. Okay. Now, I'm not going to try and draw this three-dimensional solid. So this region rotates back in, right? And we get this solid. Now, if I were looking at it from below this way, it would just look like a big circle, right? This way. But it's actually got a little funnel-shaped area, and then curves on the outside as we go around. It's kind of like a donut cut in half, but the donut doesn't have a hole in it. It's kind of like merged together as one. No hole in the center, so to speak. So what's the volume of this going to be? Well, if I were to integrate with respect to the y-axis in the disk method, I would use horizontal rectangles. Now look at the rectangles here. It would be from here to here, and the problem is I would have to get this side of the curve and this side of the curve in terms of x as a function of y, right? Because I would be integrating with respect to y, and I would have to solve this equation for x. Y equals x minus x cubed. I have to solve for x, and that's a cubic equation. It can be done, but it's not easy necessarily. And there are instances where it's very difficult to solve for x, and so you can see the shell method is going to work better. We're integrating with respect to the x-axis in this case, as we showed before. Our arbitrary rectangle, right, is vertical, and we rotate that about the y-axis. Okay, so remember the two things that we need for that are the height and the radius. So when we rotate this thing about, we're going to get a thin cylindrical shell. And there's that rectangle going around. We get this thin cylindrical shell, and right, coming right out of here, right, that's the y-axis, right? That's the y-axis. And so we've got our p of x here. That's our radius, and our h of x. Okay, so the h of x is just the height of this thing, right? That's the h, and the p of x is this distance here. But what is this distance? It's from the y-axis to an arbitrary value x, so we'll just call that x, right? As x varies from what? From 0 to 1, right? X varies from 0 to 1, so this is some arbitrary x length. So in this case, we see that p of x is equal to x. And what's h of x equal to? It's just the height of this function, right? It's just the height of this function. So h of x is x minus x cubed. And so remember, if we cut this open into the slab, then we'll have what the length will be 2 pi times p of x, 2 pi x, times the height h of x. That's the volume of the shell. We integrate that, that's the area times the thickness would give us the volume. But we're going to integrate that area from what? From x equals 0 to x equal 1. And that's going to give us the volume. So I've got from 0 to 1, 2 pi, p of x is x, times h of x, x minus x cubed dx. Now I'm just going to just set this up. You can, of course, evaluate this integral. It's not that hard. Pull the 2 pi out, distribute the x, you get x squared minus x to the fourth, and just integrate that from 0 to 1. It's pretty easy to do. so I'm not going to do that, but you can check that. But this is the shell method, and it's much easier to set up and evaluate than it would be had we done the disk method. Okay, let's look at some other examples of the shell method. We're going to do the same region, so under this x minus x cubed and y equals 0, so just this top region here in the first quadrant. We're going to rotate it now about x equal negative 1. About x equal negative 1. So now, where's x equal negative 1? That's right here. X equal negative 1, that's right there. So what's different about this now? You know, when we did about the y-axis, this rectangle went around and went back in here. So here's our thin shell. Now what's our thin shell? We go in around this axis. So our radius is much bigger now. In fact, what is our radius? Our radius was x for this one, just x. Now it's x plus what? How far is this? From negative 1 to 0. It's 1 unit. So notice now our p of x in this case is x plus 1. All right? This is x and this is negative 1. X minus a negative 1 is x plus 1, right? So this is x, this distance is 1, x plus 1 is our radius. And so this comes all the way around and then back in at a distance of x plus 1 this way. So it's a much wider, right, radius there for our shell. We've got a much bigger shell in terms of radius. But the height doesn't change, right? The height is still that rectangle, so it's the same. H of x is still the same. And so our volume is, we'll pull that 2 pi out. It's going to be very similar to this one. We're still going from where? Still going from 0 to 1 because that's the region under the curve. It's not from negative 1 to 1 because our area that we're in, rotating about this region simply exists from 0 to 1. It's just this area. So this area is going about this line. Okay. So it's still 0 to 1 and it's 2 pi p of x times h of x. What about x equal 1? What if we rotate about x equal 1? Well, let's see. Here's x equal 1. Let's see, I'll do this in blue. X equal 1. So now we're going to rotate this rectangle, right? Instead of about the y-axis or about x equal negative 1 way over here, we're going to do it about here. So it's going to go this way, right? And we're going to get a thin cylindrical shell this way. Okay. So notice in this case, this from here to here, that's our p of x. That's our p of x for this example, right? That's our p of x. The h of x is the same again. The h of x is the same. So what is p of x? Well, notice it's 1 minus what? What is this location? X, right? If this total distance here between my fingers is 1, which it is, right? From 0 to 1 is 1, and this distance from the y-axis to our rectangle is x, right? Arbitrary x value, then what's left over is what? 1 take away x, 1 minus x. So that's what p of x is down here. Okay. And so as x gets bigger, our radius gets smaller, right? And it varies from x being from 0 to 1. H of x is the same. And we're still integrating the same area from 0 to 1, right? It's going to come around and rotate into on this side, right? And we'll have that solid that we're finding the volume of. P of x is now 1 minus x, h of x, x minus x cubed. The last one we'll look at is about the line x equal 3. So I don't have, this, it would be off the page here because here's x equal 1, x equal 2, x equal 3 is way over here. But again, I'm going to rotate this same thing now. If x equal 3 is way over here, I'm going to rotate it about that, right? And I'm going to get a big long shell this way. Since this P of X was 1 take away X. This one will be what? 3 take away X. So our P of X here is 3 take away X, and our H of X is still the same. And so the volume is 2 pi. Again, integral still from 0 to 1 because that's the region, right? It's just from 0 to 1. So it's going way, rotating around into, around x equal 3. 1, 2, 3, somewhere way out here. So it's 2 pi P of X times H of X. So let's close this then with a contrasting the disk washer and the shell method. I'm going to do on the next example both methods, and just so you see, use both methods to find the volume of the solid generated by revolving the region in the first quadrant bounded by y equals x cubed, y equals 0, x equals 0, so those are the x and y axis respectively, and x equal 2, so x equal 2 is the vertical line here. So you can see that region. Okay, so first we'll do the and we're rotating it about the y-axis here. So here's the y-axis. So we want to rotate it about the y-axis. Okay, so hopefully you can visualize that solid. If I rotate this about, on the outside it looks like a cylinder, but inside we've got this bowl shape, in the middle of it. Okay, so if I start with the disk method, since I'm going with respect to the y-axis, I have to have rectangles that are horizontal, and I'm integrating with respect to y. So there's an arbitrary. So I integrate from y. Notice y goes from what? This is the x-axis, y equals 0. Where are we at up here at the top? Right, 2 cubed is 8, so this is y equal 8. So I'm integrating from y equals 0 to 8. And when I rotate this around, so our disk washer method, that's going to give me right a washer. And coming out of the center is, of course, the y-axis. And we have our smaller radius and our bigger radius. Okay, the bigger radius is going from the y-axis to the right side of our rectangle. So here's the big R from here to here. That's big R. That's that outer radius. And notice it's always what? It's on this line x equal what? 2. And so this is always a distance of 2. The capital R is always equal to 2. Okay. What about little r? Little r is from the y-axis to the left side. Sorry, the capital R was to the right side of the rectangle, and the little r is to the left side here. So this is little r. Well, little r then is what? The right-hand side is on this curve, which is the curve y equals x cubed, but I need x in terms of y, and I can solve for x by doing what? Taking the cube root. X is the cube root of y, or we write y to what power? 1/3. We write y to the 1/3 power. So that's what little r is. All right, and you can see that's true. When y is 0, the little r goes to 0, doesn't it? But as y gets bigger and bigger, that little r, as we move on, it's getting bigger and bigger and bigger. In fact, it's approaching what? 2, right at the very top. When y is 8, we should get 2. And what is 8 to the 1/3 power? The cube root of 8 is 2, right? So it is working. This is the formula we need to give us our inner radius. So now we're ready. The volume, remember? So the area is pi. So again, this is the area we're looking for, this outer washer here. So it's pi big R squared minus little r squared. Right, that's the disk washer. So our volume is integrating, we'll pull that pi out, integrating again with respect to y from y equals 0 to y equal 8. And it's capital R squared, which is 2 squared minus y to the 1/3 little r squared. And that's with respect to y. I guess we'll clean this up. We're just going to evaluate this. So I've got 2 squared is 4. And y to the 1/3 squared, 1/3 times 2 is y to the 2/3. So that's what I get as a setup. Let's go ahead and evaluate it this time and just see. We'll compare the two methods with the evaluation as well. Pi, what do I get? The antiderivative of 4 is 4y. And then the antiderivative of y to the 2/3, I add 1 to 2/3, so that's 5/3 divided by 5/3, so it's 3/5 y to the 5/3. I'm going to evaluate it at 8 and at 0. Of course, when I plug in 8, I get 4 times 8, which is, what's 4 times 8? That's 32, isn't it? Minus 3/5 of 8 to the 5/3 power. And of course at 0, it's going to be 0 minus 0. It's going to be 0 minus 0. So we just have to, so what's 8 to the 5/3 power? That's the cube root of 8, which is 2 to the 5th power. 2 to the 5th power is 32. And so I get 32 minus 3 times 32, 96/5. 32 minus 96/5 turns out to be 64/5 if you do the arithmetic there. So I get 64 pi over 5. Okay. So that is the disk washer method. Let's compare that then in closing with the shell method. Let's compare that with the shell method. Okay, so now what are we looking at? Now we're going to integrate with respect to x, and we're going to have vertical rectangles. Because this rotates around and we get a disk or a washer. This rotates around and we get a thin cylindrical shell. Okay, so we're going to get our thin cylindrical shell here. All right, about y-axis. And then remember, we need two things. We need this p of x and we need this h of x. And then the volume or the area that we're looking at integrating is 2 pi p of x times h of x. 2 pi p of x again is the circumference, but when we open it up, that's the length of that slab, if you remember, and the height h of x. So multiply the length times the height. So the h of x, again, what's the height of this rectangle here? That's the h of x. Well, it's just equal to what? X squared. X cubed. All right, the height goes from 0 to 2. The height is going to go from 0 up to what? 8, right, which is 2 cubed. So h of x is just equal to x cubed. And then p of x, right, since we're going from the y-axis to this arbitrary rectangle, that length is just x. Right, and x is varying from 0 to 2, right? So some arbitrary x value, we're going to draw that rectangle and rotate it around. And so p of x is just equal to x. And so our volume is 2 pi can come out, and we're integrating now with respect to x. So what are we integrating with respect to x? From 0 to 2. From 0 to 2. So this is with respect to x from 0 to 2. P of x is x. H of x is x cubed. And so, of course, x times x cubed is x to the 4th. What's the antiderivative of x to the 4th? x to the 5th over 5. Plug in at 2, I get 2 to the 5th is 32 times 2 is 64 pi over 5 minus evaluation at 0, which is just 0. And of course we get the same thing that we got with the disk washer method. So which method do you prefer? You might feel that the setting up the washer methods may be easier for you to set up the integral, and you're a little confused on how to get the shell method, but not too much more challenging. I think you just have to do some more examples and try. Certainly the integration seems to be a lot easier for the shell method compared to the disk washer method. Okay, so it depends on the region. Sometimes one method is preferable to the other. Other times either method is equally valid to be used in a situation. Okay, but you need to be able to use both methods as prescribed if you're asked to do it one way or the other. And so you want to definitely practice and work at lots of these examples that we have. Okay, so that is the end of our journey into volumes, and then volumes of these solids of revolutions using the disk washer and then the shell method.